Okay, so we have looked at diodes briefly. We should discuss diodes in a more detailed manner today. We will discuss it. So, what have we learnt about diodes so far? The characteristics, okay, the symbol. Okay, so if you are applying a voltage to the anode and this will pass through the diode, this is what the characteristic will be. So at 0 you see it is 0, okay, this portion here is far towards the left. If we supply a negative voltage, there is a certain point where the diode will break down. Breakdown means that it is going to get destroyed. So that's when you'll have a reverse breakdown voltage. So we have to make sure that we don't reach this point here. Okay, so this V rated is always given in the data sheets of the diodes that you are going to use. So make sure you take in consideration the blocking voltage, because after that this just becomes a open circuit, not a open circuit actually, it just becomes a wire because the diode burns, finish. So that's towards the negative side. Now moving towards the positive side, if we apply a voltage, it will start rising exponentially to a certain point, Vf, V forward. In normal cases, you remember our V forward voltage was 0.7 volts. Yes, so Vf is rated. For power diodes, you'll have different values of Vf. So make sure you look at the ratings for this in the data sheet. So V forward, once you reach the V forward point, your current will increase according to the voltage value of your supply. And then there is also a point where it can get burnt if you supply a large amount of current. But for power diodes, it's not a big problem, because for power diodes, we can cater for about more than 100 amps. So we don't really reach to that point. Okay, we are always below 100. And this was just a ideal characteristics. Okay, ideal means normally we should have this, but we don't have it in reality. Okay. Now some points for you to note down. At turn off, the diode current reverses for a reversed recovery time, TRR. Okay, that's what we were looking at. Okay, at turn off, the diode current reverses for a reversed recovery time, TRR, before falling to 0. So once you have supplied a voltage through the diode, it does not immediately come back to 0. Okay, if you are using it as a switch, okay, it does not immediately come back to 0. It needs a time, reverse recovery time. Okay, so let me write this down. So at 10 off, right, the diode current reverses for a reverse recovery time, which is known as TRR, before falling back to 0. Okay, so this means that the diode requires a negative current to sweep out the excess carriers to make it or bring it back to 0. So remember this, you cannot, the diode does not come back to 0 immediately, okay, it requires a reverse recovery time to come back to 0. This is the point that you should remember always. Now that was the power diode. We have some other kinds of diodes. So one of them is a fast, okay. So since this is a problem, recovery time is a problem, we have a fast recovery diode. Fast recovery diode, okay. So you now immediately know what the characteristics of these fast recovery diodes will be like, okay. TRR will be small, okay. So these free fast recovery diodes are used in applications such as drives, okay. In drives, this very common name is freewheeling diode, okay. And then is also another application for fast recovery diode, which is a feedback diode. What happened? Freewheeling, sorry, free, FR. Freewheeling, okay. And then we have another application, feedback diode, okay, feedback diode, okay. This is used for inverters and converters, okay, we can just say converters, okay. So we have the power diode in general, then we have the fast recovery diode, we have applications of freewheeling, okay, in drives and in inverters. Then we also have another type of diode which is known as the Schottky diode. You remember this Schottky diode? Yes. So Schottky diodes. Schottky diode. Okay, this type of diodes have the following characteristics. It has a low V forward required, okay. So if it has a low forward voltage required, so we can say that it is used for application which don't have higher voltages than about 500 volts, okay, nothing higher than that. So V forward, okay, and on the other side it has higher leakage current, okay, meaning that it can go towards the left hand side of the characteristics before it breaks down further towards the left. It is a higher breakdown on the negative side, okay. It is just like we are offsetting everything towards the left. Okay, tell me if you don't understand anything. I should improve my handwriting, yes? I can show you the lecture slides if you want. No? Okay. I'll try to improve. And the other point that I have just said is that it has a lower wattage rating. So lower wattage rating. so it cannot be used for high power, okay, applications. Okay, another important point, it has limited blocking capability. Okay, Schottky diodes are normally used for power supply applications such as rectifiers. Okay, so the application for Schottky diodes is rectifiers. So now you see where the three different types of diodes are used. Okay, power diodes are used in general. Then if you are required fast recovery diodes, then you can use fast recovery diodes. These are used for freewheeling and feedback types, okay, drives and converters. Then we have the Schottky diode, which we normally use for rectifiers because of its characteristics. So you see, we cannot use one particular kind of diode for all applications. We have different types of diodes for different types of applications. So you need to know where you are going to use which diode. Okay, you cannot just take a diode. Okay, in MATLAB you can take a diode, right? Just take a diode, do the simulation. But what about in real life? If you are at work and then you get an application to make a inverter, okay, you are going to look for a Schottky diode, okay, because of its characteristics. Okay, this is what is important for you to know. Now, something that I would like you to do during the lab, okay, to keep this lesson properly aligned, is why don't you try? Okay, I'll make a lab handout. Why don't you do applications for these three different types of diodes? Okay, use a power diode. Okay, use a fast recovery diode. Okay, all these types of diodes are available on MATLAB, and then use the Schottky diode. So the application would be, okay, let's just keep it to one. Let's use a bridge rectifier. Yeah, you think you will be able to do this application in simulation in your labs? Yes, at least see what happens when you use different types of diodes. Okay, at least you will get an idea of what you are dealing with. Okay, don't worry, this is not just one of the questions for your lab, there are others as well. So now you have your application that you can do even at home if you have time. Okay, if you are not Netflixing, then just try to make this bridge rectifier and see what are the different ways you get outputs. Now, what about diode protection? Okay, everything needs a protection from something, right? Diodes also need protection. Now, what do you think? How can we protect a diode? Okay, in general, what do we use? We use a semiconductor fuse. So if a question is asked to you, okay, how do you protect a diode? You will have a answer of, you will say to use a semiconductor fuse. Okay, in general for everything, either it's a diode, thyristor, GTO, IGBT, we use semiconductor fuse. How does a fuse act? It blows up before the device. Okay, because the fuse sees the current di over dt. What is the current flowing at a particular time, all the time. So as soon as the current reaches above the specified value or the rated value of the fuse blows up first, protecting your diode. So can you tell me, if your diode is rated to handle 10 amps of current, what will be the rating of your fuse? Something less than 10? yes, so that it does not blow up your diode. So make sure you take note of this. So protection is semiconductor fuses, and there is something else, okay, some other kinds of protection as well. So protection, so I'll put asterisk, we normally use semiconductor fuses, okay. Now this something for the protection of di over dt. When I say di over dt, I am just saying something for you, protection against current, okay. Di over dt is just current over in respect to time. Di over dt we just normally use a circuit, a inductor in series with the diode, okay. Di over dt protection. So if I ask you a question, di over dt protection of a diode, you will say a series inductor with the diode. Now what about dV over dt? Protection against voltage. So for protection against voltage, we have something, okay, a term given as RC snubber. Have you heard of this before? RC snubber? Yes, you have heard of it. You have designed last semester, E321. To protect your diode, in MATLAB there is a section where you have to fill in your RC snubber values. Yes, okay. This is the protection against RC dV over dt. So what dV over dt, okay, the circuit looks like is something like this. You have your diode, okay, you may have a inductor, okay, and your load here. Oh, sorry. Now your RC snubber comes here. Okay, this is what your RC snubber looks like. RC snubber just creates a RC time constant, allowing the voltage to flow at a particular rate. Okay, so it does not burn the diode. Okay, so now you know everything about diodes in detail. Now you should never forget the characteristics, okay, the symbol, operation, okay, what happens when you go towards the left, okay, what happens when you go towards the right. You have VFD, okay, forward voltage, and then you have reverse blocking region, okay. It is a certain point till where it can block negative voltage and then it collapses. So we don't want to reach that point. So we have to always see the ratings. Whenever you get a device, remember, whenever you get a device, first thing you have to do is find the data sheet and look at the ratings. And then you also got your lab to make the bridge rectifier with different types of diodes. Understand the types of diodes, see how these diodes work, what are the characteristics, is it very different from each other, okay. And then now you know about the protection of diodes. Diode is clear? Thank you. Now let's move on. Okay, let's see if I've got something else in the lecture slides. Okay, no, lecture slides are very discreet. So now let's move on to thyristors. Anyone knows what is the other name of a thyristor? Anyone? We have discussed this the day of introduction. Hey Fred, how are you? After a long time I have seen you. Everything okay? So thyristors are also known as SCRs. Okay? What is it? Silicon controlled rectifiers. Okay, thyristors are also known as silicon controlled rectifiers. So let's look at thyristors in detail. Okay, it's also in your book. Okay, now let's go to this document. So SCR, silicon controlled rectifiers, aka thyristors. Okay. So how is a thyristor made? Okay, if we want to see in N and P terms, so thyristor is something like this. What happened? Share with me. What happened? Okay. I should put something like this. I am very scared of my students. Also known as, okay? You know what IKM means? Yes, you know what IKM means, right? So coming back to thyristors. Now, our thyristors look something like this. Okay? First we have P, which is heavily doped. Okay? I hope you remember what is doping. Remember? Yeah, not the grog doping. N, and then we have another P, and then we have a N, which is heavily doped again. On top we have our anode, which is positive, and then the bottom we have our cathode. We are going to put it as K, and then in this region we have our gate, G. Now if we were to draw the symbol of a thyristor, the following figure simplifies to this. So we have a diode here and a gate. It is controlled, partially controlled. Okay. So A positive, okay, this side is positive, this side is negative. We have our cathode here, gate, input current IG, I gate, and here we have our current I A. Looks very similar to our diode, if only we didn't have the gate part. Now let's see what does the gate do. Before we look at the gate, let us look at the characteristics. Okay, characteristic curve. Okay, let me show it here, it's better because I think I am not a good artist. So suppose we are here at 0, okay, we got a thyristor, we brought it to our lab, now we want to turn it on and see what happens. So you get the thyristor and then you start supplying voltage at A, the anode, okay. You start from 1, 2 volts, 3 volts, 100 volts, 200 volts, 300 volts, say 500 volts. What happens? The thyristor is destroyed, okay, and then that point is called the forward breakdown voltage, okay. If you just get the thyristor and start supplying power to A, you will reach this forward breakdown voltage where the thyristor collapses and then the voltage starts increasing according to the voltage at A. So we don't want to go there. Where do we want to be? Here. A similar characteristic to that of a diode. How do we reach this point? On, off to on if Ig pulse is applied. So if we apply a Ig pulse at the gate terminal, okay, the diode starts conducting. Then we have a characteristic to that of a diode. If we don't supply this Ig current, it remains here, okay. So we need this pulse from Ig, the gate pulse, in order to reach this on state. Okay, now you understand how the on works. The reverse is very similar to that of a diode, okay. You have a reverse blocking region till a certain voltage, say for example a certain voltage which is given in your rating, 200 volts, 300 volts, negative 300 volts, okay. When you reach that point, it has reverse breakdown voltage 200 volts, it collapses, okay. Clear how the thyristor works? Yes? Any point you are not sure here on the characteristic curve? It's clear, right? And then we have our ideal working characteristic. Just simple. If it's reverse blocking, it will block till infinite. Forward blocking, it will block till infinite. And in on state, it will go high, the voltage, the current, okay. So now we understand the characteristics. What else can I tell you? Okay, you know the symbol now, you know the characteristic. Only control for turn off, okay. Something to note down, okay, let's note it down. Putting it in red so you remember. Thyristors, so are only controlled for turn on, not turn off. That's why thyristors fall in the semi-controlled, okay, semi-controlled devices, because we can only control it to turn on, but we cannot control it to turn off. So what happens? What happens in the off region? Okay. So once the device begins to conduct, okay, it is new term latched Okay, latched L. Latched on the gate current. Okay, what does this mean? Once you turn on your thyristor, okay, once you turn on your thyristor here, once you give a, you are giving a voltage at the anode, then you give a pulse G, right? Once the current starts flowing from A to B, it is independent of the gate pulse. Either the pulse is on or off, it does not care. The current will flow. Okay, the current will flow till when? Okay, let's see given here. Yeah. So this is the example. But before that, let's continue to write few more things. Let me write the point that I have just said. Cannot be turned off by gate. Okay, cannot be turned off by gate only when the anode current tries to go negative, the thyristor will turn off. Okay. So for example, if we are supplying DC voltage at the anode, I don't think the thyristor will turn off. Okay, because DC always stays positive unless you apply negative DC voltage. But if you are applying IC, you have continuous positive and negative, so it's easier to turn off the thyristor. That's why for thyristor the applications are only for, again, we only use applications where we go from IC to DC. Again, IC to DC is a rectifier. So rectifier operation. So rectifier application. And also put it in red. Do not use for DC input circuits, because it's hard to turn off. Reason being, only when the anode current tries to go negative, then the device will turn off. If we have a DC supply, then we'll need a auxiliary circuit to bring it. Auxiliary circuit means another circuit to just bring it from positive to negative. Okay. What do you think? You can do this in the lab? Yes. You can also see, you can make a rectifier. Okay. The same rectifier, the bridge rectifier, because you are going from IC to DC. Use the thyristor. Okay. So this is another lab. You will be using a thyristor for a bridge rectifier. Okay, what else? Let's see the circuit. Okay, a example is given here. Okay, let's see what I've written here. Semi-controlled, as I've said, only you can only control it on the on time, not the off time. Latches on by a gate current. pulse if forward bias. To turn off, it requires, okay, reverse. Current tries to reverse, okay, negative, that means negative current. Thyristor in a simple circuit, you see here the input is AC. It is trying to convert into DC. So this is our Vs, okay. This is what the output of the thyristor should look like. This part here and then 0. Okay. Try to make this circuit in your lab and see if you get the same output. Yeah, you can do that? Yes. And then again, similar fashion to the diode. In a simpler fashion to the diode, we have the reverse recovery time, okay, TRR here. But we also have something else. We have the turn off time interval TQ. Please make note of this. Okay, TQ is the turn off time interval. Okay. Why turn off time interval? Because we will be supplying, you see, a negative current. Okay. Once we have supplied the negative current, it takes some time for it to go back to 0. So this is done automatically in a diode, TRR. But for a thyristor, we have TQ. We need to supply, or the circuit needs to have negative current in order for it to go to 0. So this time is said to be TQ, turn off time interval. Okay. Point here says for successful turn off, reverse voltage is required for an interval greater than the turn off interval. Okay. We need to supply negative voltage in order that the thyristor is 0 again. Okay. Open again. Let's put a summary of the thyristors. So, to turn off a thyristor, it is not so easy. Okay. That's why we use it in a DC to AC application, such as a inverter. We can also use it as a DC-DC converter, right, Chopa? So DC-DC application also works as long as the input is DC. The thyristor is okay. Okay. Oh, sorry, it's the other way around. Yeah, IC to DC. Okay. So not used yet, not used. Okay. Not used for these types of application. Okay. So big no. Converter application and Chopa application. We are going to use it for IC to DC, where we have voltage reverse. Okay. It is voltage reverse, so we can have a natural turn off. But for these applications, we require a circuit to turn off. Okay, you know what natural turn off means, eh? Because we have IC, we automatically go to the negative region. So we are supplying negative to the thyristor in the negative cycle. So the thyristor automatically turns off. The TQ is met, the turn off time interval. For that particular interval, we are supplying negative voltage. The thyristor turns off. And then in the next cycle, we can give the gate signal for the thyristor to turn on. Okay? Clear? Yes? Jibril? Okay? Okay. No one looks confused. Now turn on is very easy. Okay? For turn on, we just need a forward bias. Okay? This means voltage at the anode should be greater than the voltage at the cathode. And we need a gate pulse. Okay. When I say gate pulse, this means that the gate terminal has a higher potential than the cathode terminal. Okay. Another point, very important. When we are turning on, we have to remember the latching current that we have discussed. Okay. So, current needs to be the latching current, that is anode current should be greater than the latching current. Okay, because once the thyristor is turned on, it won't turn off until the latching current is there. So the anode current needs to be greater than the latching current for it to turn on again on the next step, next cycle. And in the turn off position, to turn off, we need the current anode. Okay, the current anode should be less than the current holding. Okay, so the current holding means the current that is inside the thyristor. Okay. And then says needs to be reversed biased at least for the turn off time interval, that is TQ. Last thing for thyristors is protection. What do you think? Semiconductor fuses. Okay, we are going to use semiconductor fuses. So the task that you have received today is to make a bridge rectifier using diodes, the 3 different types of diodes that we have talked about. Also use a thyristor, and for the thyristor you also have to make the circuit that has been shown in the lecture notes. This, try to see what you get.